Hey folks, welcome to my channel number 10. There we have the problem on our screen. Examine the differentiability of the function in R by drawing the diagrams, right? And we have two functions which have been given to us. One is a mod sin x function and the other is a mod cos x function, right? So we've been asked to examine the differentiability, remember, not from first principles, but by sketching the graph, right? And we know the definition of a mod function, and we have the mod of sin x here. And please remember that whenever you have a mod function, the mod function will always be positive, right? So a mod of x is always positive, and therefore a mod of sin x is also positive. So I can write the function in a very similar way that I do when I rewrite the function for a mod x, right? And we're going to do the same thing for mod of sin x. And so my mod of sin x equals sin x for sin x greater than or equal to 0, and it's equal to a minus sin x for sin x lesser than or lesser than 0, right? So let's look at how the graph of sin x looks, and I'm going to do a rough sketch of this, right, for us to understand how the graph of sin x looks, and then from there we will move on to mod of sin x, right? So I know that my sine of 0 is 0, and my sine of pi and sine of minus pi is also 0, right? So how does this graph actually look? This is how my sine x looks like, right? And for sine x greater than or equal to 0, and let's kind of use a highlighter here, our function remains the same, right? So which is that? It is this regions, right, where your sine x is positive, right? So we don't have to really worry about the regions highlighted here in green. And whenever my sine x is negative, which is probably, let's use a different color, let's use say red, right? Oh no, let me use a lighter color, say pink. It is this region, right? The region belonging to, for example, 0 to minus pi, and then pi to 2 pi, and then minus pi, minus 2 pi to minus 3 pi. All these regions are when your sin x is negative, right? So what happens is when I have a mod function, right? The mod function says whenever sin x is less than 0, please represent it as minus sin x, right? That is what is the definition of a mod function. So what happens, the mod sin x for these regions, right, minus 2 pi to minus 3 pi, or 0 to minus pi, or pi to 2 pi, etc., does not, change in shape, but it just switches its direction, right? So what happens, if I may take my green pen, maybe this region becomes something like this, right? Right. So what happens, you remember mod of sin x is never negative, right? So these regions which we have highlighted in pink, are now represented by the green curve, right? Green curve. So I hope you understood how this function mod of sin x gets transformed from sin x, right? So I wanted to start off with sin x and showcase how this particular diagram looks like, and now I'm going to rub this off and directly go and let's see how our mod of sin x looks, right? So this is how our mod of sin x will look like, folks. So the function is throughout positive, and there we have the diagram on your screen. And similarly, the function repeats itself in the entire domain of R, right? So we're not going to draw that, we're not going to show that. So the way this looks like is the function undergoes a transformation in direction at these points, right? I'm just circling them, folks. Similarly, you will have here. So at minus pi, minus 2 pi, minus 3 pi, and then at pi, 2 pi, 3 pi, and so on, you will see that this particular function has a very sharp edge, right? Which you may call it as a cusp or a corner, and which means that the slope of this particular curve mod of sine x undergoes a change in direction as we move through these points, which is 0 pi 2 pi 3 pi and so on in the positive quadrant of x, and then minus pi minus 2 pi minus 3 pi and so on in the negative quadrant of x, right? So uh, I'm sorry, in the negative direction of x. So we can generalize this, right? So I know that my function undergoes, or rather I would say comes to a sharp edge at the point x equals n pi, right, where n belongs to the world of integers, be it positive or negative integers, right? So what happens is at these points the slope of the tangent to the curve undergoes a change in direction, right? And like we saw in our previous video, these points x equals n pi are sharp edges for the curve mod of sine x, right? Therefore, we don't have to go and explicitly work this out using first principles. We can comfortably conclude that the function is not differentiable, right, at the points x equals n pi, right? And how do we write this? We write this like this, right? Function is not differentiable at x belonging to n pi, and n belongs to the world of positive and negative integers, right? And why is that? Because at these points are sharp edges, corner or cusp, where slope undergoes a change in direction and hence not differentiable, right? So that's how we arrive at the differentiability of this function. And with this, we will move on to mod of cos x. So folks, there we have our mod of cos x written for us on our screen. So mod of cos x, uh, the way we write this is very similar to how we write a mod function. That equals cos x for cos x greater than or equal to 0 and minus cos x for cos x lesser than 0, right? And so my cos function looks like this, right? My cos of 0 is 1, my cos of pi by 2 is 0, my cos of minus pi by 2 is also 0, right? And then the function takes minus 1 at pi, and then it goes like this, right? And similarly on the negative direction it takes a minus 1 at minus pi, and then it goes like this, right? And my cos of 2 pi is 1, right? So this is how the function looks like. And so when you look at this, what is this point? This point will be your 3 pi by 2, right? And similarly this point is my minus 3 pi by 2. right? So what happens is, like we saw in our mod X, let me use the highlighter. When I, this region, right, these regions where my cos x is negative, right, which is in the interval pi by 2 to 3 pi by 2, which is my open interval, right? Because at pi by 2 and at 3 pi by 2, the function is 0, right? So in the open interval pi by 2 and 3 pi by 2, and similarly minus pi by 2 to minus 3 pi by 2. So these regions, right? So when my mod of x, mod of cos x equals minus cos x for cos x lesser than 0, means the regions highlighted in green uh, will now just undergo a switch in direction, right? So because my mod cos x function is always positive, right? So what happens? This portion, right, which is highlighted in green, is going to look like this in my mod function, and similarly on the negative direction of x as well, right? So that's how it's going to look. And so my graph is going to look like this, right? So my graph is going to look like very similar to mod of sin x, but then the sharp edges, right, which we saw in mod of sin x, which occurred at pi, 2 pi, 3 pi, etc., is now going to occur at pi by 2, 3 pi by 2, 5 pi by 2, and 7 pi by 2, right? Similarly, I've got minus pi by 2, and then minus 3 pi by 2, and then minus, uh, minus 7 pi by 2, minus 5 pi by 2, and so on, right? So let's redraw this graph. I hope you understood the transformation from cos x to mod of cos x, right? So that's what is important. And I want you to understand why the graph of cos mod of cos x will look the way it's going to look now when we sketch it out, right? So this is how my mod of cos x looks like. And we can definitely identify which are those sharp edges, right? And I'm just going to quickly circle them out here. Let's take our, yeah. So my function has sharp edges at these points, right? And pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on in the positive direction of x. And then I have minus pi by 2, minus 3 pi by 2, minus 5 pi by 2, and minus 7 by 2, and so on in the negative direction of x, right? So these are my sharp edges. And what are these sharp edges? These sharp edges are where my slope of the tangent to the function undergoes a change in direction, right? So my left hand derivative and my right hand derivative at these sharp edges are not going to be equal because they're going to change direction. They're going to be of opposite sign, right? And some books refer this as a corner, some books refer this as a cusp, but for now let's call them as a sharp edge, where we know for sure that the slope of this particular slope of the tangent to the curve changes direction at these points, right? Now looks like we can generalize these points, and we can definitely call them as x belonging to, and if I can pull out my equation, my x belongs to 2n plus 1 1, 2n plus 1. And what is 2n plus 1? My odd integer set, right? And multiplied by pi by 2, right? So at all points 2n plus 1 pi by 2, we know that the slope of the tangent to the curve at these points undergoes a change in direction. My LHD is not equal to my RHD, right? My right hand derivative is not equal to my left hand derivative at these points. And let's call them sharp edges, right? You may call them corner of cusp. And function is therefore not differentiable, right? At right. That completes our solution to this particular problem. I hope you found this video useful. Please do subscribe to my channel and support. Thank you.